Have you ever driven down a perfectly flat highway that just slices right through the middle of a massive rolling mountain range and thought, how on earth did they actually do this? Well, let's dive right into it. Welcome to today's Explainer, where we're going to unpack a truly fascinating tool that transforms the chaotic, messy, and incredibly expensive job of construction into a perfectly balanced mathematical equation. Today, we're looking at the Mass Hall diagram, which is quite literally the blueprint for moving mountains by the numbers.
I mean, think about it. How do engineers efficiently move millions of tons of dirt without completely breaking the bank? It's honestly one of the biggest logistical and financial nightmares in all of civil engineering. When you're building a new road, a railway, or really any massive infrastructure project, you aren't just paving over what's already there, right? You have to literally reshape the earth. And since every single cubic yard of dirt you move costs serious time and money, you definitely don't want to move the same pile of dirt twice if you can avoid it. You need a master plan.
All right, Section 1, Moving Mountains of Dirt.
So the ultimate solution to this giant logistical puzzle is something called the Mass Hall diagram. This is basically a graphical tool used in civil engineering to represent the cumulative volume of earthwork along a project's entire alignment. Think of it like a strategic visual map. It helps engineers identify cut and fill balances, calculate exactly how far dirt needs to travel, and dramatically minimize construction costs. Instead of just guessing where all that dirt should go, they use this diagram to map out the absolute most efficient, cost-effective routing for every single scoop of soil.
Moving on to Section 2, Anatomy of the Diagram.
Building this thing is actually pretty straightforward once you get the core components. First up is the x-axis. This horizontal line tracks our physical journey right along the road's alignment. Engineers usually call this the chain age or stationing. It's the physical distance. Then we've got the y-axis. You can think of this vertical line as our dirt bank account. It tracks the cumulative volume of the earthwork. And finally, the all-important zero line. This is our baseline, our break-even point. Whenever our graph touches this line, it means our dirt checkbook is perfectly balanced.
Which brings us to Section 3, Decoding the Curves.
Now, when you look at one of these diagrams, the rising and plunging lines tell a very specific story. A rising curve, that represents a cut or an excavation. Think of it as income. We're cutting through a hill, generating excess dirt, and our dirt bank account is going up. But a falling curve represents a fill or embankment. That is an expense. It means we've hit a valley or a dip that we need to fill in to make the road level. So we're running a material deficit and spending our dirt. So up means we're gathering dirt from a hill, and down means we're dumping it into a valley.
And this brings us to the absolute sweet spot, balance points. A balance point is the exact location where that curve crosses right back over the zero line. This is a moment of perfect harmony, meaning the total volume of the cut and the total volume of the fill up to that specific point on the highway are perfectly equal. The dirt we excavated perfectly filled the holes in the valleys. With zero dirt left over and no extra needed, that is the ultimate goal of efficient earth moving.
Let's get into the dollars and cents in Section 4, Distance, Dollars, and Dirt.
Okay, so you can think of the free haul distance, or FHD, exactly like a free shipping minimum when you're shopping online. In construction contracts, this is the agreed-upon standard distance that excavated material can be transported without incurring any extra financial charges. The contractor has basically baked the cost of moving the dirt the specific distance right into their baseline price. It's the standard zone where they'll move the material before the proverbial taximeter starts running.
But here is the crucial question. What happens when you have to move that dirt further than the free zone? Well, that is called overhaul. Overhaul is the extra charge zone for moving material beyond the free haul distance. And let me tell you, this is where project costs can absolutely skyrocket if they aren't managed carefully. Every single foot of overhaul is an extra line item on the invoice. But thanks to the Mass Hall diagram, project managers can clearly see exactly where overhaul is going to happen long before the first bulldozer even turns on its engine.
Now, what if the whole project just doesn't balance out perfectly? Well, then we enter the pretty terrifying scenarios of borrow or waste. If our graph drops below the zero line and just stays there, it means we've literally run out of dirt. We have more valleys and hills. In this case, we have to borrow material, meaning we have to buy and import dirt from a completely different location just to complete the fills. On the flip side, if our curve ends way above the zero line, we have waste. We cut through too many mountains and have a huge surplus of dirt. And we can't just leave a giant dirt mountain on the side of our brand new highway, right? So we have to pay trucks to haul it away and waste it. Both borrowing and wasting are incredibly expensive, which is exactly why optimizing this diagram is so vital. All right, wrapping things up with Section 5, Building Smarter, Not Harder. So, to put it all together, the mass haul diagram basically dictates absolutely everything on the job site. First, it minimizes costs by telling contractors the absolute most economical direction to push the excavated dirt, like whether to drag it forward down the highway or push it backward. Second, it calculates haulage. It gives the exact, undeniable data needed to compute those expensive overhaul contracts without any guesswork. And finally, it handles equipment planning. It helps fleet managers figure out, hey, do we need massive articulated dump trucks for long hauls here, or just a few bulldozers for short pushes? It orchestrates the capacity, the travel paths, really the entire logistical ballet of the construction site. It really leaves you wondering, doesn't it? The next time you are cruising smoothly down a perfectly level road, surrounded by deep valleys and massive mountain cuts, will you picture the invisible math that moved those mountains to build it? Every smooth ride we take for granted is the result of this unseen, elegant planning, balancing cuts and fills to reshape the literal earth beneath our tires. It's just a brilliant reminder that sometimes the absolute most impressive feats of physical engineering start entirely with a few lines curving on a piece of paper. Thanks so much for joining me to explore the mass haul diagram today. Stay curious, and I'll see you in the next explainer.